So hi everybody, this is Miss Doherty. Tonight I'm going to give you a little background that will allow you to complete the pre-matter walk-around worksheet. If you take a look in your notebook, you'll find the handout that shows a picture of a periodic table and a few spots for you to take some notes. And you'll actually be coloring in or labeling large parts of this periodic table to use when you complete the matter walk-around. Now the matter walk-around is going to have a number of questions about the elements on the periodic table, but it will also ask some questions that you'll be needing to refer to this handout for. So take a moment, you're going to need something to write with and also something to color in, not too many colors. We have a few things to outline or to shade in that identify different regions on the periodic table. And again, take a second to go grab those before we get started here. Okay, so I'm going to assume that you've done that. So let's take a look at what it is we're going to do first. We need some definitions, and so what we'll start with first is the name of the horizontal rows on the periodic table. Remember, horizontal goes left to right. Those are called periods because the periodic table expresses or exhibits something called periodicity, regularly repeating patterns in the physical and chemical properties of the elements. The vertical columns are called either groups or families, and the name family comes from the fact that just like members of an animal family or a plant family or a human family, the elements that are in the same column together often exhibit similar chemical and physical properties. So having located those, what we're going to do is identify the first four groups, remember, vertical column for groups, on the periodic table. And all you need to do is to turn your sheet sideways and write in the fact that group 1 are called the alkali metals. Now, if you look at the numbers at the top of this periodic table, this is a more modern version in that it goes from Arabic numbers 1 through 18. But in other periodic tables, sometimes called older versions but still just as useful, you'll see Roman numerals and combinations of those with the letters A or B. Now, in the next column are the alkaline earth metals. The alkali metals are pretty soft, reactive, crazy, wild bunch of metals, but the alkaline earth metals, while they are also fairly reactive, are a little bit calmer. And you will see that these properties of the alkaline earth metals and the alkali metals are in fact a function of their number of electrons that they have, especially their outermost electrons. Now there's a large number of columns that aren't named on the periodic table. So we're only going to identify the four that our book mentions, and the second to the last column over on the far right hand side are called the halogens. And the halogens are a group of non-metallic elements that can have various forms, solid, liquid, or gas, and have wide variety of properties. Finally, you probably know the name of the last group. On Roman numeral column 8A, or Arabic number 8, are the noble or inert gases, sometimes called the aloof gases. And the reason why they're noble or inert or aloof is because they don't tend to react with anybody. That's why it took a long time to discover them, because they were so non-reactive that they were sort of hiding in plain sight as we began to identify all the elements. Those four columns, or groups or families, actually have names. The remaining columns, such as what you see here in the top from group Roman numeral 3 through 6 or 13 through 16, we're going to call those by the element at the top of the column. Now we'll catch up to these next large group. Now the periodic table can be broken down into larger areas, 3 in fact. And one of the larger areas are the transition elements or transition metals. They are located in this region that you see outlined here. So take a moment to outline those. These are metals that have the properties of metals: shiny, they have luster, they're good conductors of heat or electricity, malleability, ductility. Remember, ductility is the ability to be stretched into a wire. But what's interesting about these transition elements or metals is, see this little gap right here? What we actually have is another subset. These two rows at the bottom actually chemically fit in top of this space here and that space there. If we were to put these two inner transition element rows into the periodic table, though, it would stretch it out into what we call the long form, and so it's not as convenient to have it all fit on like an 8.5 by 11 roughly sheet of paper. So we pull those two groups out, and even though they're part of that major area of the transition elements or metals, we're going to call them the inner transition metals. And they're sometimes also called the rare earths. It's not so much that they're rare, it's just that they are so similar in properties to each other that it was often difficult to separate them and identify them as individual elements. So here is the first row. The groups together, or excuse me, the two rows together are called the inner transition elements. So this row and that row together have a name collectively, the inner transition. And the first row is called the lanthanide series. And each of the row names is based upon the element at the front of the row. So lanthanum is the first element in the lanthanide series. Now fitting into the spot right below it, technically, is the actinide series, which is the elements that begin with actinium. So the two rows together are called inner transition. They're part of the transition metals. They're called rare earths because they were difficult to separate from each other, and they contain a lot of elements that are very important in electronics, in your cell phone, in your iPad, your iPhone. These elements are incredibly important because they help form the electronic circuitry of these wonderful devices that we have now. Now we can take the periodic table and categorize it into three main categories: metals, nonmetals, or metalloids. So metal, shiny, ductile, malleable, good conductor of electricity. Nonmetals, none of those things. And metalloids, as the name implies, are those elements that have properties that are intermediate between metal and nonmetal. And interestingly enough, they group themselves pretty nicely into distinct regions on the periodic table. Now the outline says make your metals or nonmetals green, outlined in green. But you can use any color. On this PowerPoint outline, you can see that we've taken a line that's green and we've embraced or encircled these elements that you can see in the upper right corner. So it includes the noble gases, most of the halogens, and a few other guys in columns 14, 15, and 16 that are parts of groups that don't have names. But if those are our nonmetals, can you think of another element that should be included in the nonmetal that's not in that clump in the upper right? I hope your eyes look to the left because sure enough, that's where our element hydrogen is. And that's the thing about the periodic table. It's not always perfectly organized in a logical fashion that you would like to rely upon 100% of the time, but it is organized based upon the behavior of the elements, and that is a function of their electron configurations, which we will be studying soon. So the reason why our buddy hydrogen is over here in the far upper left is because at times it acts like it has an electron to donate like the rest of the alkali metals. So even though it is not a metal, it's been placed over here on top of the alkali metal column. There are nonmetals. We're going to color in a little staircase in red or any color that you might have available. And as I begin to punch in these metalloids, or sometimes called semi-metals, you can see we put them in what we call the staircase region because it forms the buffer between the nonmetal, typically upper right corner, and everybody else who are all metals, except for, of course, hydrogen in the upper left. So these metalloids, or what we call semi-metals, have properties that I said that are intermediate between those of nonmetals and metals. So they're kind of shiny, but maybe not as shiny as a full-blooded metal. And they kind of conduct electricity, but not as good as, say, copper or silver, which is the best conductor of all. And you probably have heard the term semiconductor, and that is a term that's been used to describe the industry that sprang up out of Silicon Valley. Elements like silicon and germanium can be sort of conductors of electricity, which proved to be quite useful for electronic microcircuitry. So that metalloid staircase blocked out in red is the group or the groups that include the elements that are semimetals or metalloids. Now besides semimetals or metalloids, nonmetals, and everybody else that are metals, you can also look at the periodic table, and sometimes they're arranged in such a way so that you can tell the form of matter at room temperature. Room temperature is like 20, 21 degrees Celsius or like 70, 72 degrees Fahrenheit. And so what we're going to do now, if you look at the periodic table when we're done, most of our elements are solid metals, but there's a few that stand out. And the first two are just the two that are liquids, which we are going to outline in blue. And so we have mercury, a very interesting metal that's a liquid at room temperature, located here. And we also have bromine, a nasty smelling, horribly poisonous halogen that's located third down in its group. These are the only two elements that are liquids at room temperatures. Sometimes a few periodic tables put gallium in there, but I don't know why, because gallium has to have like the warmth of a human body, which is, in Fahrenheit is like around 98, 99 degrees Celsius, to be able to melt. So for our purposes, mercury and bromine are our two liquid elements. Obviously, we could have gaseous elements. You're breathing some right now if you're alive. So we're going to put some very small dots. Maybe you can also lightly shade it in if you just have a pencil and like to do that, on all the elements that are gases. When we're done, if you're not outlined in blue and you don't have some little dots on you, then you have to be a solid. And most of the elements on the periodic table and in the universe are solids. So here's all our gases. Please don't limit yourself just to the noble gases that you see me sort of punching in right now, because besides that column of noble gases, we have a few other gases like nitrogen, oxygen, fluorine, and then over on the far left-hand periodic table side, you're going to see our element of hydrogen. So don't forget, you've got hydrogen over here. You also have a few other gases that are here in the halogen column and also in non-named columns. And then you've got our noble gases. And those are the elements that are gases at room temperature. So taking a look at the periodic table, looking at the two different categories, because they're metal, nonmetal, metalloid, or solid, liquid, or gas, you can see that most of the elements in the universe are solid metals. Now, one of the things that people get confused about is they think that nonmetals all have to be gases. Well, notice that you can have a liquid nonmetal, bromine. You can also have solid nonmetals, like below bromine, you'll find iodine. So don't think that nonmetal means gas. Nonmetals can include solids, liquids, or gases. Now, as you do the walk around, you will also see a few cards that ask if reactions are exo or endothermic. We'll spend an entire chapter studying energy changes. But exo means, if you've heard of, say, exoskeleton on, say, insects, exo means on the outside or to the outside. So thermic has to do with heat. When you reach new or look at new terms in chemistry, try to break them down into parts that make sense for you. Exothermic reactions release heat. And either there'll be an obvious release of heat, like, say, our magnesium burning, or they could be a subtle release of heat where you feel a test tube into which you've mixed two substances and it's feeling hot. The reverse of that would be endothermic, and endo means to bring to the inside. Endothermic reactions feel cold. And they would typically be something like if you're out on the field and you twist your ankle when you're running for track or cross country, and the coach brings out one of those ice packs or instant ice packs. Well, it's not ice in there. When you crunch those chemicals, you mix together some ammonium salts with water, and that simple process of dissolving makes that bag feel cold, and you can put it on your twisted ankle and take away some of the pain. Endothermic reactions feel cold because they're going to require a net absorption of energy, and they have to get the energy from somewhere, and they get it from the environment around them. So we call the system where a reaction takes place, maybe that might be what's happening inside the test tube, and the surroundings are everything else. So if you have to absorb heat from the surroundings and put it into this chemical reaction, that's why the test tube feels cold. Now more on that later, but we will define those and explain those in much greater detail when we study heat. And I think that should just about wrap it up for your pre-matter walk-around. Remember to bring this handout with you when you answer the questions, as well as don't forget, you have that cute and smart partner. Take care.